Soil lecture number 3, soil index properties or soil plasticity. Plasticity of soil is an important property of soil, especially when we are talking about fine-grained soil and especially when we have clay in our soil. Plasticity is defined as the ability to deform a material without appearance of cracks. So deform a material without cracking. In order to look at the plasticity of a soil sample, first we need to go over the 4 states of cohesive soil. So based on the water content, we are looking at water content. We have a completely dry sample, which we call it solid, and then we start adding water. So this is increase in moisture content or in water content of soil. With a solid material, a dry material, we have the solid state. Then when we start adding moisture, the state changes from a solid state to a semi-solid state. Then if we keep adding moisture, then it's going to change into a plastic material. And by adding more water to soil, the state changes from a plastic state to a liquid state. So liquid state is when we have high water content. Plastic state is when soil deforms without cracking or rupture. Semi-solid state is when cracks are appearing in our soil. So we have development of cracks when deforms. And then solid state is when sample is completely dry and very crumbly. These are the 4 states of cohesive soil based on water content. Now we have these 4 states. We want to look at the limit. At what water content, exactly at which water content the state changes. Liquid limit is the state, the limit between liquid state and plastic state. Liquid limit, here this is water content at which soil changes from liquid to a plastic state. This water content is called liquid limit. Then we have plastic limit here. Again, pay attention that this is also a water content. But at this water content, the state changes from a plastic state into a semi-solid state. And it's called plastic limit. And the third one is here, which is a water content at which soil changes from a semi-solid material to a solid state. So this one is called liquid limit. When it changes from liquid to plastic, the water content at which soil state changes from liquid to plastic. This one is plastic limit, the water content at which the state of soil changes from a plastic state to a semi-solid state, and then we have shrinkage limit, a water content at which a state changes from semi-solid to solid. Another parameter that's important for us is plasticity index. So what is the range? Within that range, soil has a plastic state. This is called plasticity index or PI. So this range from liquid limit to plastic limit is called plasticity index, which is the numerical difference between the liquid limit and plastic limit. So plasticity index, the range within that range, soil is a plastic material, is liquid limit minus plastic limit. And remember, this is the direction where we have an increase in water content. So this is LL, this is PL, and this is SL. So LL is always larger than PL and larger than SL, which means that PI is always a number higher than 0. So it's always a positive number. And that's an indicator for the plasticity of fine-grained soil. And it corresponds to the range in water content or moisture content over which the soil remains in the plastic state. So that's plasticity index. These are called Atterberg limits. That's the name of the person who developed these limits and these tests, and we refer to these limits as Atterberg limits because they were defined by a name that the person named Atterberg. Liquid limit and plastic limit are important to understand the stress history and general properties of soil met with construction. So this is a number that we will use later in the soil classification lecture to come up with a symbol that is used to classify soil sample. And again, this is very important when we have cohesive, fine-grained soil that has clay. So these are the 4 states. And this is the direction where we have increase in moisture content or water content. And the state changes with drying, and this is the direction of drying. And one more important thing is that when we have a solid material, when there's no moisture, with drying, there is no change in the volume of soil. Volume of soil is constant. But after this point, which is our shrinkage limit, with increase in moisture, we will observe an increase in volume. This is the PI range or the plasticity index, PI, plasticity index. So the next thing that we will go over are the Atterberg limit tests, specifically liquid limit and plastic limit tests. ASTM D4318, a standard test method for liquid limit, plastic limit, and plasticity index. This is what we will go over, and this is lab 2. There is also an ASTM designation for the shrinkage limit test, but we're not going to go over that for this class. This is what we will cover: the tests that are used to measure and calculate liquid limit and plastic limit of a soil sample. So what we need, the equipment or apparatus required includes a balance, the liquid limit device, a grooving tool, mixing dishes, a spatula, electrical oven, and plastic limit device. But before going over the liquid limit and plastic limit tests, let's review the water content calculation. Water content for all materials: concrete, brick, CMU, aggregate, soil. It's always calculated as weight of moisture or water divided by weight of dried sample. That is the general formula to calculate moisture content or water content. So you need to see how much water you have in your sample, then dry your sample, divide weight of water by weight of dried sample, and you have your moisture content. So in order to calculate water content of sample, what you can do in lab is start by measuring weight of an empty container. So this is an empty container. You measure weight of empty container. Then you put some of your wet soil in the container and measure weight of container plus wet soil. Then in order to dry your sample, you leave it in an oven. We do oven drying. And now you have your dried sample. So what you measure is weight of container plus dry soil. Weight of container, WC, weight of container. Weight of container plus wet soil. And then we have weight of container plus dry soil. And then you use this formula to calculate water content or moisture content. So let's go over an example. We have, this is weight of empty container. 3 grams. Then we have weight of container plus wet soil, 65 grams. Then we put our soil sample with the container in a microwave and start drying. First we dry for 3 minutes, then measure weight of our container plus the sample and have 52 grams. Then we do another 2 minutes of drying and measure weight of sample again. So you see that the weight is going down. It means that the moisture is being removed. We do another cycle of drying, another 2 minutes, and remeasure weight of sample, continue with that with another 2-minute drawing, and we see that now weight is constant. So we do another cycle and we see that weight is still constant. When we have a constant weight, it means that all the moisture is removed. So now we can use this number as weight of container and dry soil. So this is weight of container plus dry soil. And then you just put the numbers in the formula. And we have moisture content or water content of this soil sample as 55%. So next, how we're gonna do the liquid limit test. We want to determine liquid limit, which we use LL to show that. So first we need to prepare our soil sample. We need fine-grained soil, so we need to use the appropriate sieve to separate fine material for liquid limit and plastic limit tests. Then you start gradually adding water. So we don't want to add too much water. We start with a little bit of water and then mix it properly. So for this test, you need 250 grams of air-dried soil passing sieve number 40. This is what we use to do the liquid limit test. This is the liquid limit cup. So this is the liquid limit cup. And it has a handle. So you turn the handle, the cup is lifted and then it's dropped from a certain distance. When you turn the handle, it will lift the cup and then it will drop the cup. Then we have two different types of grooving tools. We have a flat grooving tool or a wedge grooving tool. And these grooving tools are used to make a cut in the soil sample that we have. After you mix your material with water and you have like a paste, then you use a spatula, this is called a spatula, and place your soil in the Casa Grande cup. You need to make sure that you don't put too much material in the cup. It should be up to here. And the depth should be about 8 millimeters. Then you use the grooving tool to make a cut in the center of soil. Again, make sure that you don't put too much material in the Casa Grande cup. It should be like half to 1/3 of the cup. Depth shouldn't be more than 8 millimeters. And you make a center line in your soil paste. So it should be like that. You have a clear area. You make a cut in your soil sample. Then you use the handle to lift the cup and drop the cup. You need to remember or record the number of drops that is required to close. So we made a cut here. You need to count the number of drop that is required to close the cut that you made for 13 millimeters or ½ inch. So we count number of blows or number of drops as n that is required to have a clear, visible closure of 13 millimeters. It helps if you start in a way that your first n value is above 35. So this is 13 millimeter visible, clear 13 millimeter closure or half-inch closure. That's when you stop and you write down n or number of drops. So we have number of drops. We need to calculate moisture content of this soil. And that will be our first data point. How do we measure water content? You need to get a container, get some of the soil from here into the container. You have weight of empty container, weight of container plus wet soil, and you dry your sample and find weight of container with dry soil, and you calculate moisture content. That's our first data point, but we need at least 3 data points for this test to be able to find liquid limit. If the n that you have here is between 20 to 40, collect the sample from this area to do the moisture content calculation. And then you need to, as I said, you need at least 3 data points. So we need to repeat this test 2 more times. Depending on the first number of drops that you have, you need to dry your sample or add more water to your sample and repeat the test. We need again at least 3 trials, 3 data points. Why do we need that? Because liquid limit, or LL, is defined as water content at which the standard groove will close a distance of half inch or 13 millimeters at the bottom of the groove at exactly 25 number of drops. But we don't know how to do that. We don't know how much moisture we can add so that it exactly get the 13 millimeters closure with exactly 25 number of drops. So what do we do instead? We repeat the test 3 times. We have 3 data points. Then we fit a line to those 3 data points and find at 25 number of drops what is the moisture content. So our horizontal axis is number of drops. Here we have water content. We are looking for this number. That's our liquid limit. Again, because we cannot do the test in a way that makes sure that we exactly get 13 millimeters closure at 25 number of drops, we repeat the test 3 times, collect our 3 data points, fit a line, and then find our liquid limit. So when we're done with the 3 trials, then we will have 3 data points. At each data point, we have a number of drops and a moisture content, corresponding moisture content. Then we fit a line to these 3 data points. Liquid limit is defined at water content where we get the 13 millimeter closure exactly at 25 number of drops. So we find 25 number of drops on our horizontal axis. Draw this line until it intersects with our fitted line, and from there we move to the water content line. This is our liquid limit. Water content at which the cut that we make is get like visibly closed for half inch or 13 millimeters with exactly 25 number of drops. So LL is 46.4%. This needs to be done in Excel. So we collect 3 data points. Each data point is a number of drop and corresponding water content. So trial number 1, trial number 2, and trial number 3. With 30 number of drops, we have water content of 45%, 23 number of drops, water content of 47, and 18 number of drops, water content of 48. We have these numbers in an Excel file. We select the numbers, go to Insert, Chart, then click on the triangle for scatter and select scatter with only markers. And that's what you get. 3 data points on your chart. Then you need to add title axis, the title for your horizontal and vertical axis. So horizontal is number of drops, vertical is water content. Then you need to add minor grid line. So you go to minor grid line and select vertical minor grid line. And then you need to set your horizontal axis to a logarithmic scale in a base of 10. Then you have this chart, and now we need to fit a line to our data points. So you click on your chart, go to add trend line, and then select logarithmic. Also put a check mark in front of display equation on chart. That is your line. We have the formula of line, so there are 2 ways that we can find our liquid limit. The first one is just find 10, 20, this is 25 number of drops. So draw a line from here to your curve and then go here, and that's our liquid limit, which is approximately 46.4%. Or we can use this formula, the formula of the line that we fitted to our data points, and substitute x with 25. So here, instead of x, we put 25 in our formula, and we get the exact liquid limit. This one has a higher accuracy. This is ln. If you have that in your example, just know that ln is natural logarithm, which is the logarithm of a number in the base of e, constant e. So make sure that you use the correct sign on your calculator. Next, we need to find plastic limit. Plastic limit is the water content at which a thread of soil begins to crumble when it's manually rolled out on a glass plate to a diameter of 1/8 inch and breaks up into segments about 1/8 to 3/8 inches in length. If your sample is too wet, then the thread can be rolled to a smaller diameter, smaller than 1/8 inch diameter. That means your sample is just too wet, so you need to dry it. And if the sample is too dry, then you cannot roll it to 1/8 inch diameter, which means that the plastic limit has been surpassed. So you have your soil sample, you start adding moisture, you need around 20 grams of materials passing from number 40 for plastic limit. You get a glass plate, that's what we need for peel. Get some of your soil sample and start rolling it into a thread. Again, if you can roll it to a thread with a diameter lower than 1/8 inch, it means that it's too wet. If you cannot get to 1/8 inch, it's either that you have a material that doesn't have plasticity or it's too dry, so you need to add moisture to it. So what we are trying to do is to roll it into a thread with 1/8 inch diameter. You keep doing that until you see cracks appearing. So you get samples from where you see cracks appearing in your sample and calculate water content of this sample. Water content of this sample is our plastic limit. So let's go over an example. We have the results for the liquid limit and plastic limit tests. Trial number 1, trial number 2, and trial number 3. For each trial, we have a number of drops and a water content. Also, the result from plastic limit provided. The question is asking us to draw the flow curve and find liquid limit. Also calculate plasticity index, which is liquid limit minus plastic limit. So you have your data points, you prepare your curve, moisture content, number of drops, you have the formula of line, substitute X with 25 and you get your moisture content, your liquid limit. Liquid limit is 32%. So from here, we calculated liquid limit as 32%. Now we want to look at the plastic limit result. We said that we try to roll our sample to 1/8 inch diameter and then take sample from where we see a crack and calculate moisture content of this sample. Weight of container with wet soil, and weight of container with dry soil. We calculate water content of this soil sample, and that's our plastic limit. So we have 38, weight of can and wet soil, weight of empty can, 12, and weight of can and dry soil 35. You put them in the formula and you have your plastic limit. Knowing liquid limit and plastic limit, you can calculate plasticity index as liquid limit minus plastic limit, which is 19%.